Okay, so in this section, we're going to use eigenvalues and eigenvectors of the coefficient matrix of a linear system of differential equations in order to actually create the solutions, the general solution, to that particular system. Okay, let's motivate sort of why this is going to be a thing that works, and at the same time come up with an actual process of sort of steps to solve these problems. So to do that, let's take a look at a problem that we already have solved. So let's recall that we saw the general solution to this particular system here. Okay, so we understand the basic theory of general solutions to systems with respect to the fact that there's going to be n of these specific solutions here of this form, where n is the dimension of this matrix here. However, the question that's not yet answered is, are they all going to have the form of an exponential right here? So are they always individually going to be just like a constant times a vector times an exponential? In particular, is that always going to be an exponential? And the answer is basically yes, except we know that the exponential function sometimes is hiding other functions like sine and cosine. So we will come across those instances, and probably no surprise, that's when we have imaginary numbers that we're working with. So to proceed, let's make the assumption that we have a specific solution to a system and that it is of the form e to the lambda t. Okay, so here we're just going to call this vector here capital K, and the elements of capital K are these lowercase k values subscripted 1 through n. So we can write this as capital X equals, of course, capital K e to the lambda t. And if we take the derivative of both sides with respect to t, we would get the vector capital X prime, which is equal to, well, the lambda comes down, and now we have capital K e to the lambda t. Okay. However, recall that capital X prime is equal to ax. So we have ax is equal to lambda capital K e to the lambda t. Okay, but recall that x is equal to k e to the lambda t. So we can replace x here with that. All right, now we can certainly divide both sides by e to the stuff, because that's never ever equal to 0. And that gives us a times the vector k is equal to lambda times the vector k. But this is exactly the form that tells us that lambda is an eigenvalue of the matrix A, and at the same time, k is an eigenvector of the matrix A. So if we're looking for a solution to this particular system, all that means is we just have to find lambda and capital K, and of course we just figured out that lambda is an eigenvalue of A and capital K is a corresponding eigenvector. So the question just becomes, find the eigenvalues and eigenvectors of A. All right, so we've basically punted the entire problem of solving a system of linear homogeneous differential equations to the problem of finding eigenvalues and eigenvectors of a coefficient matrix. So that makes this a very straightforward process. So let's get into some examples. Okay, yeah, we've seen this particular system a number of times in different contexts, and of course we've solved it, like I said, a long time ago in using the differential operator, the capital big D notation. And now we're going to solve it much more efficiently by finding eigenvalues and eigenvectors. So the first thing we're going to do is make sure that this is in normal form, meaning that the derivative is isolated, which it is. Okay. So now we're going to form the matrix of coefficients, that capital A. Okay, so that's just going to be these coefficients, 4, 7, 1, and -2. And okay, all we're going to do is find the eigenvalues and corresponding eigenvectors of A. Okay, so we know that that involves rooting out the characteristic equation, so that's the determinant of capital A minus lambda times the identity matrix, so that's this determinant here. All the entries that are along the main diagonal will have lambda subtracted from them. And of course we're going to get a polynomial here. Taking this determinant and foiling this, we get okay, and this one even factors, so that's going to be helpful to us because we'll be able to get the eigenvalues pretty much by looking at it. Of course, when it doesn't factor, you need the quadratic formula. Duh. So we can see that this gives us lambda equals -3 and lambda equals 5. Okay, we are now going to find an eigenvector for each of these eigenvalues. And the eigenvector that we find, that'll be like the capital K that's associated with each of those. Now there are many capital Ks. There's many eigenvectors associated with any given eigenvalue. So we just need to get one though. And the simplest way to do that is by looking at this determinant matrix right here and setting any of these rows, doesn't matter which one you pick, equal to 0 when multiplied by little k1 and little k2. So let's do that. Okay, so for the first eigenvalue that we found, let's let lambda equal -3. And let's lift this row out here. So we're going to have the row 4 minus lambda times little k1 plus 7 times little k2. That's going to give us 0. So we're just going to solve for k2 in this situation. And that's not going to be too bad. But remember, we need to replace lambda with the specific lambda here, so -3. So right here we have 4 minus -3, which is 7. So 7 little k1 plus 7 little k2 is equal to 0. And if we solve for k2, we can see that k2 is equal to little k1. So that means that we can form an eigenvector, and the eigenvector, of course, will be capital K1, and it'll consist of little k1, little k2, and we can pick any numbers we want as long as it satisfies this condition. So we might as well pick k1 to equal 1 and k2 to be -1. But you could pick k1 to be 7 and k2 to be -7 if you wanted. So that's crazy, but you could do that. Okay, notice that this actually corresponds to a solution here. We have now the solution, capital X is equal to capital K1 and then e to the lambda t. So that would be 1, -1, and then e to the -3t. So that's going to be one of the terms in our general solution. And to get the other term, we just need to do everything we just did, but with the other lambda value. So we'll go with lambda equals 5. So you can use the same initial equation, or you could have gone with row 2 if you wanted. Again, you get exactly the same constraints. So plugging in lambda equals 5, we get 4 minus 5, which is -1, little k1 plus 7 little k2 is equal to 0. And so we get 7 little k2 is equal to k1. And so k2 is 1/7 k1. So that means that the capital K2 vector is going to be, again, we can pick any numbers we want to go in there as long as they conform to this pattern here. So K2 has to be 1/7 of K1. So you could pick K1 to be 1 and then 1/7 down there. That's perfectly good. I'm going to just go with picking K1 to be 7, and so K2 being 1/7 of that will equal 1. And this gives us the other solution. So that's going to be capital K2 and then e to the lambda t, and lambda was 5. Okay, so these are the two solutions that we found. And as it turns out, producing solutions this way will guarantee that these are linearly independent. And of course, we have the right number of them. So putting these together as a linear combination with arbitrary constants will be the general solution to the system. All right, and because math wins all the time, we of course get that this set of solutions is consistent with our findings from earlier analyses of this problem. Okay, so here we have a system of differential equations we want to solve. Cool. So let's first extract the coefficient matrix. Okay, very good. And now we will find the eigenvalues and eigenvectors. So again, we're going to start by finding the determinant of the matrix obtained by subtracting lambda from the diagonal entries. So yeah, we're going to get this. Okay, so a little foliage here gives us a 5 plus 5/2 lambda plus 2 lambda plus lambda squared, and then minus 3/2. Okay, so now let's set this equal to 0 and solve for lambda. Okay, so not clear if this factors. Let's double everything. We can safely do that. Okay, yeah, this does factor. That'll do it. So we're going to get a lambda value here of -7/2 and another lambda value of -1. So great, let's just find a corresponding eigenvector for each one of those and form our general solution, and we'll be done. Okay, so yeah, just pick any of the two rows, and let's just pick the first one again. So that would give us -5/2 minus lambda multiplied by little k1 plus 2 little k2 is equal to 0, and we'll just kind of solve this for k2. So letting our lambda be -7/2 and subtracting that from -5/2, we would just get 1. That's nicer than I expected it to be. So here we get little k2 is equal to -1/2 k1. So that means that our capital K1 vector, which is of course this little guy, is any pair of numbers that satisfies this condition. So you could let little k1 be 1 and then little k2 be -1/2, but why don't we keep everything all integer happy, and let's let little k1 be 2, and so little k2 will be -1. This induces the solution capital X1, which is now going to be this, is 2 -1, and then e to the -7/2 t. All right, so let's just find the other one. So of course we're going to now let lambda be the other eigenvalue that we found, which is -1. So -5/2 plus 1 is -3/2. Okay, so little k2 is going to be 3/4 of little k1. So therefore the vector capital K2 is going to be any pair of numbers that satisfy this. So why don't we let this guy be 4 and this one will have to be 3. So those are nice numbers. And that means that capital X2 vector is this thing. Okay, so now we're ready to put together our general solution. So that first one was this. And the other one was this. And there we are. Much, much better than mucking around with the differential operator, isn't it? Okay, so life is merry with this process. But what if the eigenvalues are complex? Right? This is a complication that we can deal with. And the following result here is going to be stated without proof. The actual proof of this is not overly complicated, it's just very tedious algebraically. It involves lots and lots of Euler's identity, working out e to the I theta in terms of cosines and sines, and reshuffling around of all those terms, and reassigning of constants as we go, and so on. And it's just, it's much worse than any other proof that we've seen related to turning complex solutions into cosines and sines. So let's see what we're working with here. So let's suppose that we have a complex eigenvalue. So we've got a lambda is equal to alpha plus I times beta. Okay, and specifically beta is not equal to 0. So this is not a real number. Okay, and let's say it has a corresponding eigenvector, capital K1. Well, the issue here is that the eigenvector K1 will also have at least one complex member in it. And that's something we don't want to deal with. But what we can do is we can separate the vector capital K into two component vectors called B1 and B2. So what I mean is, for example, suppose capital K1 is the vector 1 and then like 3 plus 2i. Okay, then what we would do is, for a moment, we're going to write this 1 as 1 plus 0i, as it is, and we would split this into a B1 and a B2, where we have B1 being 1, 3, and B2 being 0, 2. Okay, so this is like our B1, and this is like our B2. And of course, B1 plus B2i is equal to the original K1. Okay, but these B1s and B2s are what we're going to be using in the formula that's about to be written down. So the way we express this idea is by writing B1 and B2 in terms of what are called the real and imaginary parts of the vector K1. So we're going to let capital B1 be the real part of the vector K1. So that's what this RE means. It means the real part of the vector K1. And at the same time, we'll assign capital B2 to be the imaginary part of the vector. Okay, then these are the ingredients we're going to use to form the general solution. So the general solution is going to be, of course, as usual, C1 times X1 plus C2 times X2, where capital X1 is going to be capital B1 cosine of beta t minus capital B2 sine of beta t, and this is multiplied by e to the alpha t. And x2 is, now be careful with this because this is a capital B2 here, cosine of beta t plus capital B1 sine of beta t, and again, all multiplied by e to the alpha t. So there it is. This is how we form the solution in the case where the eigenvalues are complex. You may notice that we only needed one eigenvector k1. We didn't. What about the other eigenvector we always get, right? Well, it turns out that when you have complex eigenvalues, that they occur in conjugate pairs, and correspondingly the eigenvectors also occur in conjugate pairs, which means you only need to analyze one, and the other one is predicted, which is exactly why we only look at one of them. We only look at the capital K1 here. So, and we form the B1 and B2 from it, and from those we form our general solution. So definitely, obviously think this is a great idea to go into an actual example where we do this, and you'll see that really this isn't so bad. Okay, so here we have a system of differential equations to solve. And we're going to go find the eigenvalues and eigenvectors and la la la. I sure hope they're not complex. Well, let's see what we're working with. So first of all, let's determine our A. Okay, very good. So now we will find the eigenvalues and eigenvectors. Or as my friend Glenn would say, find all the eigenthings. All right, so now we have our characteristic polynomial. Let's set it equal to 0 and solve for lambda. Pretty sure this is not going to factor, so we will use the quadratic formula. So 4 squared is 16 minus, every poker player knows 4 13s is 52, and that's all over 2. So we have 4 plus or minus 16 minus 52 is negative 36. Of course, that's 6i all over 2. So we have 2 plus or minus 3i. Oh no, they're complex. Well, no problem. We know how to deal with that. So we enter the universe of handling this as a complex eigenvalue, which means we don't need to find two eigenvectors. We just are going to look at the one eigenvalue 2 plus 3i and find the eigenvector associated with that. And then we'll find our B1 and our B2, and we'll just sort of shove those into the formula and we'll be done. Okay, so looking at the determinant matrix, we can just extract the first row, and we have the equation 1 minus lambda times little k1 minus 2 times little k2 is equal to 0. And we'll replace lambda with this thing that we found. And we have to be very careful with our parentheses here. So cleaning up the inside here, we get 1 minus 2 is negative 1, and that negative also distributes like this. So let's be very careful here. Moving that over to the other side gives us 1 plus 3i times k1. And dividing by negative 2, we get negative 1/2 minus 3/2 I times k1. Okay, so we can put our k1 together here. Let's be very careful doing this. So let's just let the top here be 1, and the bottom is going to be negative 1/2 minus 3/2 I. Okay, so now we're going to find our B1 and B2. And recall that B1 is the real part of capital K1. So again, the real part is the terms without the I, right? So this is just going to be 1 and negative 1/2. and b2 is the imaginary part of that vector k1. So that's the parts that do have the I. And remember that 1 is written as like 1 plus 0i. Any real number is written like that. And of course, a complex number is a little more transparent about what its pieces are. So we're going to have the imaginary part of 1, which is 0, and the imaginary part of that bottom thing, which is negative 3 halves. Okay. Notice that we don't have an I here. B1 and B2 are both real valued vectors at this point. Okay. All right, so before we go into our x1 and our x2, let's just quickly recall that we're also going to need the fact that we used this particular lambda, which was 2 plus 3i, because that tells us that alpha is equal to 2 and beta is equal to 3. In fact, you can think of those as the real part of this and the imaginary part of this, as we've been using that all along. So now we have all the ingredients we need. Let's go in and just fill in those formulas. Okay, well, capital X1 is equal to B1 cosine of beta t minus B2 sine of beta t, and multiplied by e to the alpha t. So we have all of those pieces. Okay, so this is capital B1 was 1 and negative 1/2, and beta was 3. Capital B2 was 0 and negative 3/2, and alpha was 2. So technically this is our x1, but what we want to do is actually write this entire object here as a single vector. So this is going to be a 2x1 vector, and the first entry at the top here is going to be this thing. So 1 times cosine minus 0 times sine. So in fact, that's just a cosine of 3t, of course. The bottom entry will be this whole thing here. So it's going to be negative 1/2 cosine of 3t, and then plus 3/2 sine of 3t. Okay, so there's our x1, and it's exactly the form that we would want. It's a vector times, e to the 2t. So we'll do the same thing to find capital X2. Remember, the formula is a little bit different. Okay, and let's combine this entire object into a single column vector. Okay, so we're going to have sine of 3t in the first entry, and in the second entry down below we'll have this thing. Okay, very nice. So we now have our x1 and we have our x2, so we can put them both together as a linear combination, constant times 1 plus constant times the other, and we'll have, of course, our general solution. So the form is, of course, capital X is C1 x1 plus C2 x2, and that's going to be this lovely thing. All right, so there it is. There's our final answer. And that completes the course content.
Get used to it.